Okay, so learning outcome 14 is our definition of acceleration. So acceleration is a change in velocity per unit of time. E.g. an acceleration of 5 meters per second squared. So we write that as ms to the minus 2. And that means that the velocity increases by 5 meters per second each second. So that's why we have the per second bit twice. Once for the speed bit, which is the meters per second, and then the idea we're looking at that change in speed each second. Negative values indicate a decrease in velocity or deceleration. And it's the same formula for both. That's v minus u divided by t. Work out the change in velocity, divide it by the time, because it means change in velocity per second. So A is acceleration. And we're using v and u because we've got two different speeds or velocities. Remember we said that in these examples, speed and velocity will be the same because we're not going to ask about acceleration where something's changing direction as well. So up to now we've just used v to mean velocity, but in these examples we've got two velocities, so we need to use different letters to distinguish between them. And just if you think about the alphabet, u comes just before v. So u is the velocity at the start, or the initial velocity, and v is the final velocity. And t is the time measured in seconds. And we're going to deal with standard units in this. So I was just working out there quickly. You would be expected to be able to convert that anyway. 60 miles per hour is about 27 meters per second. And anyone interested in cars? Anyone know how long a car might take to go from 0 to 60?
If you're talking sports cars, it's about 2 seconds.
Right, the fastest sports cars in the world, you're talking about 2 seconds. Okay? So let's take that as an example. Now, standard problem solving technique. What information am I given in the question? Now, looking back over the question, you can see we've got this 27 meters per second. We're going to ignore the 60 miles per hour. That's not a standard unit, but because we're given it in meters per second. But what am I going to list that as? Is that the final speed? Is that the initial speed? 27 meters per second. So the final speed, v, is 27 meters per second. I'm given the time is 2 seconds. And you agree that's all the information at first glance that appear to be given in the question. But this is a key idea that when you're doing problem solving, not every bit of information is listed as a number. Can anyone tell me what other bit of information is given in this question? It's given in word form. Sean?
Initial velocity, which is rest.
Right. It says it starts from rest. That's quite a common way that you'll find in questions. So from that, from those words, you can fill in that u is 0. Right? So if you think you're missing data, sometimes it's worthwhile going back through the question and seeing if it's there in words rather than in numbers. And standard problem solving, what am I being asked? I'm being asked acceleration. So this is a fairly straightforward one. No rearranging of the formula required. Plug in the values. We know what is what we've been asked. 27 minus 0, all divided by 2. Now just watch when you put that into your calculator. If you literally just put into your calculator 27 minus 0 divided by 2, your calculator will do the 0 divided by 2 first and give you the answer 27, which is not correct. Essentially what you need to do is either put brackets around the 27 minus 0 or calculate it and then do answer divided by 2. Okay, so you've got to watch that one. So the actual correct answer there is 13.5 meters per second squared. So that would be a large acceleration. That's larger than the acceleration due to gravity, for instance. Okay, so example 2. So a realistic value for, say, a family car might be 2.5 meters per second squared. And we'll just base it on the same numbers as before, because quite often when you're going to buy cars, this is what they quote. It's 0 to 60 time. And once again reminding ourselves that 60 miles per hour is 27 meters per second. You're not expected to be able to convert miles per hour. Kilometers per hour, yes, but not miles per hour. So once again, if we list what we know, in this example we're given the acceleration. That's quite obvious. And we've got from 0 to 60. So u straight away we can see is 0. If it's 0 in one unit, it's 0 in all units. And v, we want to use the meters per second version, not the miles per hour version. And we've been asked how long will it take, so we've been asked a time. Same formula as before. Substitution's different. We've got the value on the left-hand side. We put my brackets around my 27 minus 0. Okay, so I've done my substitution. Next thing you want to do is to simplify what you can. So we can work out that bit in brackets, can't we? It's dead easy. 27 minus 0 is 27. So we're just going to rewrite that in a slightly different form, or simplified form. 2.5 equals 27 divided by t. But what I'm trying to work out is t, and that's in the bottom line. That's the kind of worst case scenario in terms of the reorganisation that you're going to have to do. I will need to get t off of the bottom line. So the first thing I'm going to do is to multiply both sides by t. Okay, so on the left-hand side, that gives me 2.5 times t. And the whole point of that was on the right-hand side, the multiply by t cancels out with the divided by t and leaves me 27. Now, I've still not got to a stage where I can get the final answer yet, but I'm getting closer. So I've got to go through that step. Everyone follow that step okay? Anyone want to tell me what I'm going to do next then? So divide both sides by 2.5 because that will give me t on its own. Cancels out on that side, and I get my calculator out and do 27 divided by 2.5, and I get the answer 10.8 seconds. Learning outcome 16 is describing the experiment. Right? So how would you measure the acceleration of a trolley, right, in a lab? Right? So thinking about the apparatus, basically one of the best ways to think about this experiment, and quite a lot of experiments, is to think about the formula that's kind of behind it. The formula we've just introduced then is this A equals V minus U over T. So if you want to get a value for A, you're going to need a value for V and U and T. Okay? T is quite straightforward. We can use timers to measure times. How do we get values of V and U? Now they're instantaneous velocities, remember, and we've already given you a learning outcome about the idea of how you can use a single light gate to get an instantaneous velocity. But we need to do that twice. We need to do it for the initial speed and for the final speed. Okay? So our apparatus is going to involve our trolley rolling down a ramp. Our trolley needs a mask on top of it. So I'm going to label some things. So that's our trolley. A mask or a flag. We need 2 light gates. And it doesn't really matter how you draw your light gates, as long as you clearly label them. And then lastly, these light gates need to be connected to some sort of timer. So it doesn't matter if you've gone through a Bluetooth adapter and connected to your iPad to use as a timer. The marker in an exam isn't interested in that. All they are interested in is the idea that you know you need some sort of timer. So set up the above apparatus, and one thing we've just got to be clear about we've got to be clear that the mask has got to interrupt. The light beams in both light gates. There's no point in setting up that apparatus with the light beams up above the height of the mask, for instance. You wouldn't get any data. Then we get down to the detail of what measurements we need. We need the length of the mask, which we can simply get using a ruler. And then we've actually got quite a lot of times involved. Right, so I'm going to, I should have measured the length of the mask using the ruler. I'm going to call that S, sorry, just at the end of that line above. Put in brackets S. Measure the time for the mask to go through light gate 1. I'm going to call that T1. Light gate 2. I'm going to call that T2. And between the light gates, and I'm just going to call that T without any subscript. And all of those times are measured using a timer. So that's all the measurements we need. Calculate the initial velocity u using S and T1, so the time through the first light gate. And I'll just put in brackets there, that would be, the calculation would be u equals S divided by T1, just working out the instantaneous velocity at the first light gate. We're still doing calculations now. The final velocity, which for us is the velocity at the second light gate, the symbol for that is V. And for that we need S and T2, so V is S over T2. And then once we've done all that, then we can get the acceleration. There's quite a lot to that experiment.